very much. Thank you very much for being here, for the invitation. I'm very happy to be here. A few minutes ago, Jose was explaining me what was the way which this seminar works. And he was telling me that I had the option to speak and ask for the questions later, or to accept to be interrupted. And I said that, above all, it's up to you. But being me, the speaker, and Mark, my dear friend Marco, one of the listeners, it has no sense to ask for the questions to be later.
You have no real option.
You're not in charge.
He certainly will interrupt, and I'm happy to for that. Okay. Well,
So I will try not to interrupt you, as I'm exemplifying.
Okay. Well, as Marco has just explained, my talk will deal a little bit about what is going on in Euclid's elements. I will concentrate only or mainly on the first book of the elements. I will say something concerning the book 2, which is the global content of my first book, which is dedicated to study the books 1 and 2. But at the very end, I will say something maybe related to what will happen in book 3. Okay. Well.
So your first book is on book 1 and 2.
Exactly.
So we can expect 6.5 books.
Something like that. Okay. Well. Before I begin, I want to say that I've heard a lot of very interesting stuff here during these 2 days I've been here. I've heard many very interesting things which have helped me and have given me some really interesting insights. Yesterday in Marco's class, he said something about possible characterization of mathematics, and you said, Marco, that was given by Descartes, which says something that as mathematics is very easy locally, but very difficult globally. I mean, understand locally what's going on in the proof of the proposition theorem. It's quite relatively easy to follow. But the difficulty comes if we want to have a general scope, a vision of what's going on globally. Okay. And so, according to this, that is a very interesting image of one of the first, the oldest, it's a piece of, it's almost to say it's a manuscript. It's just a piece of scroll, including we can recognize. Do we have a pointer, something like that?
No.
Yeah,
I have, right?
So,
I think.
If there's no this.
Sorry, I don't have it.
Okay. The second one is very well. It's a well-known manuscript. Wonderful. The second one is a well-known manuscript known as the Vatican manuscript, which is the main source for the actual edition of Euclid's, the official edition of Euclid made by Heiberg. Okay. What really interests me is that quotation made by historian of mathematics, Wilbur Noor. He said something really interesting. I think you can read it. We have never had a genuine text of Euclid, and maybe we will never have it. Not in the Greek version of PP is the manuscript, the Vatican manuscript without us. T means the collection of Theoninian manuscripts, and B is the collection of manuscripts around the so-called, those which are the Bodleian manuscripts. And not in any of the medieval variations either. We have no idea really of what really Euclid did. What I love is the last sentence. but we can do much better than has been done so far. The first thing is we will try to understand what's going on in Euclid. But many questions I think that can be raised concerning whenever we intend to provide an interpretation of Euclid's elements. I think I'm in particular interested in something concerning the foundations of Euclidean geometry. Because, you know, a classical question concerning philosophy of mathematics is precisely the question concerning the foundations of mathematics. But let's do it, raise the question in a more narrow way concerning the foundations of Euclidean geometry. And my first question, if it is possible to say something concerning the foundation of Euclidean geometry, starting from the source of Euclidean geometry, I mean, from Euclid's text itself. A lot has been said concerning this particular stuff about around what we could say the axiomatic framework underlying Euclid's elements, particularly the role played by the postulates and the common notions. This morning I heard a lot of very interesting stuff concerning that. But I would like to say concerning that something which I said yesterday, that it seems to me quite easy, it's relatively easy to say that starting from this axiomatic framework, it's quite easy to develop the content, the geometrical content of books 1, 2, maybe 3 and 4. But the geometrical content of book 6, that means the content related to the theory of similarity of figures, it's not so easy to say that it follows easily from this axiomatic framework. Something is needed in order to develop the theory of similar figures. Some ancient commentators of the elements, for example, Aaron of Alexandria, Theon of Alexandria, Paris of Alexandria, Proclus, they all tell us about the existence of previous geometric texts previous to the elements. And I'm discussing this lately, recently, at lunch today. I was talking about this particular stuff because we know by reference existence of these books, but really we do not have a clear idea of what these geometric texts, pre-Euclidean geometric texts were organized. I mean, this difference are just underlined between the geometry of congruent figures and the geometry of similar figures. This division, which, roughly speaking, we can say between what is the developed by Euclid in the first 4 books, what is developed in book 6, this is the geometry of similar figures, and we know that between them is book 5, which develops the theory of proportions, which is needed besides the axiomatic framework developed, presented in book 1, is needed in order to develop the theory of similarity of figures. What I want to say is that this division is clear for us in Euclid's elements. We have no idea at all, and we will never have an idea of, for example, how was organized a geometric text, a geometric treatise, as, for example, the one of Hippocrates of Chios. We know he had, Proclus tells us about the text, the geometric text of Hippocrates of Chios. It's not sure at all that Hippocrates had this division, this distinction between a geometry of congruence, a geometry of similarity. This is clearly stated only by Euclid. For example, when in his book on the commentary of the first book of the Elements, Proclus comments on every proposition. Book 1, he is very detailed and he says, and certainly he's true, he's right. He tells us about this division, for example, proposition 5, proposition 15, proposition 26 of the first book of the Elements were already known by Thales of Miletus. Propositions 32 and 44 were known by the Pythagoreans, and propositions 9 to 12, 18 to 20, 22, 25 were known by Hippocrates of Chios. That is true, well, maybe true, maybe yes, certainly yes. But we do not know in which order these propositions appear. I will not speak in which order appear the propositions 5, 15, or 26, because there is no existence, we have no notice about the existence of any geometric treatise written by Thales of Miletus. So what does it mean that Thales of Miletus knew this proposition? Certainly no clear idea. The same happens with the propositions 32 and 44, which Proclus claims were known by the Pythagoreans. How come that? What kind of knowledge did they have about these propositions? Concerning this group of propositions, which were known by Hippocrates of Chios, there we must say, well, maybe they appear in the book, in the treatise of geometry that was written by Hippocrates of Chios. That's maybe it's true, but in which order? If Proclus is right, that these propositions were there, but in which order? We have no way to accept or say that they appeared precisely in that order. Okay. Even though we still know that, for instance, from Simplicius, in his that's a very indirect way, because we know Simplicius made a commentary on the physics of Aristotle, and in this commentary on the physics of Aristotle, he reads what he talks about the text of Hippocrates of Chios, but in the way in which it was transmitted by the pupil of Aristotle, his okay, well, so it's quite interesting, indirect, these source also. But before we claim that that Euclid provided a new and maybe more accurate proof or version of all these propositions, we should ask what I have just pointed out. Exactly what was the role and of this proposition, of these propositions in the pre-Euclidean treatises, and wonder if it was the same role that these propositions play in Euclid's texts. Therefore, an answer for the initial question concerning the foundations of Euclidean geometry, we think we should, before asking for the role of the axiomatic framework, we should ask about what I've just pointed out. I mean, the role of some of these propositions. What role these propositions play, if they all play any role at all. Okay? And I think that we should maybe wonder if some of these propositions and other propositions in the book of Euclid played some guiding role. I mean, they could be considered as guiding propositions, which somehow give us the path of what is going on in Euclid's text. These guiding propositions, if they exist, I could consider them in this sense somehow of fundamental propositions. Okay, so in this sense, I want to raise a question concerning the role of some fundamental propositions, elements. Okay, as I said before, the geometry concerning the relation of congruence and equality for plane figures could not be guided in the same way as the geometry concerning the similarity of these plane figures. So the guiding propositions or fundamental propositions should be somehow different. Okay? Let's take an example. For me, and this is not an initial proposition of book one, but it's a later proposition of book one. It's a wonderful proposition, I think. It claims that triangles are half of the parallelograms. It could be a very simple, trivial relation, but let's think about all what is needed in order to prove that this relation is true. We know that this relation is true in Euclidean geometry, but we know it does not hold in hyperbolic geometry. It does not hold in elliptic geometry. Therefore, something happens in Euclidean geometry in order that this proposition holds. So I think that it would be nice to try to follow this path. I mean, what is needed in order to prove this? If this proposition is somehow a relevant proposition. Maybe it's worth to follow this path from the author of the elements and claim that the paths that give us the key or the clue for this, the propositions that give us the clue for this path may be considered as fundamental. I think that the starting point for this path is provided by number one, the proposition which claims that what's up here? Okay. So I would say it really easy. The proposition that claims that if this side, for two triangles, this side is equal to this side, this one is equal to this one, and this angle is equal to this one, then the two triangles are congruent. Okay. This is very well known. I would say only the enunciation of the theorem. It's really a lot of things that must be said concerning the proof of this theorem. I think that it is not an accident, and that's the only thing I would say. It is not at all an accident that this proposition just mentioned in Hilbert's Foundations of Geometry is not a theorem, but an axiom. So I think that something really interesting happens there, but I will not mention, will not go on, and I will go quickly to the second proposition, which I think is important, which is the following to the first congruence theorem, this one, which we all know claim that in a isosceles triangle, the angles opposed to the equal sides are also equal. Very well-known proposition, but I think it becomes a key proposition in the path that I want to follow. Why? just to make a small remark. According to Aristotle, this proposition was very, very well known, and Aristotle give us a proof of this proposition in the prior analytics, paragraph 24, if I'm not wrong. Okay, and the proof is somehow this one. What I want to say is the following. In order to accept this proposition, well, let me complete this. We have a circle, we have an isosceles triangle. These two lines are diameters. Hence, this angle and this angle are equal, as also this angle and this angle, because are angles of semicircles. That is the first claim we should accept. Also, this angle and this angle are equal because they are angles of a circular segment. Hence, two equal angles are subtracted, therefore, this and this.
So here you're using angles that are not really.
They are mixed angles.
Right.
They are mixed angles. But not only this is used in the, let's say, Aristotelian, which is not really Aristotelian. This is a proof that Aristotle tells us. It's not from him. What I want to say is that in order to accept this proposition, some stuff concerning the geometry of the circle should be accepted, recognized, or maybe proved. We know that Euclid does not recognize or does not accept this proof. Because mainly, that is another interesting question that can appear concerning the proposition I am discussing. The fact that it's very interesting. What is the role of the circle in book one? In book one, the circle has been used, is used all through book one, but not a single geometric property of circles is used. Circles are used only in book one and in book two, only in order to obtain from certain line segments, equal line segments. A property that comes directly from the definition of what a circle is. But no geometric property of the circles is used by Euclid. Here, I am using quite some properties, geometric properties of the circle. That is one of the reasons I might say Euclid does not accept this proposition, this proof. I mean, maybe it's worth remembering too, very, very quickly, Euclid's proof.
What you're saying is that in the first book, the circle is only used as a construction instrument.
The circle is just a constructed device, if I might say.
Yeah.
Okay, no.
But the fact that the lines are not straight lines is not a problem for Euclid. Euclid defines angles and then he defines rectilinear angles.
The fact is that there is no proof that the mixed angles, which legally exist from the very beginning, are equal in the case of semicircles, but they are equal in the case of circular segments. That is what is proved in the previous, is used in the previous proof, and it's not accepted by Euclid in book one. I was saying, when we want to prove with the means of the first book, which are very poor, let us remember that it is proposition number 5 of book one, the one I'm talking about. And the only theorem that has been proved is the first congruence theorem. the side theorem. It's the only thing that Euclid has at hand. Now, what does Euclid do? Once again, a very interesting thing that I heard this morning is we can do that, and we can do that, and we know that this is a straight line, this is a straight line, we are following postulate number 2, and this is equal to this, these two are equal, therefore this and this are equal. Okay, this angle is the same for these two triangles. Let me put the blue triangle and the black triangle in order to recognize them. It's quite easy. So because of proposition 4, the side angle side theorem, the blue triangle and the black triangle are congruent because they have an equal angle. This side in the black is equal to this side in blue, and this side in blue is equal to this side in black. Therefore, this base and this base are equal. Also, this angle and this angle are, this angle and this angle are equal. Once again, because this and this are equal to this and this triangle and this triangle are equal. Hence, this angle here is equal to this angle here. Therefore, this angle and this angle, which already proved to be equal to these angles, we subtract these new equal angles, hence this angle and this angle are equal. And we have proved this. So you could say we do not need, and it's not justified to use in this proof, in the proof of this proposition, anything concerning the geometry of the circle. The only thing we have used is this theory. Okay. Now, I just want to raise a question. It's the same question I raised yesterday in the meeting with the students. It puzzles me a lot, the following thing. The next proposition, after 5, is proposition 6. And what does proposition 6 of Euclid's element says? It says that if in a triangle these angles are equal, hence the sides, opposite sides are equal. What puzzles me a little bit, maybe I'm completely wrong, what puzzles me a little bit is that anyone accepting, knowing, believing in this theory should imagine something about this one. Okay? According to Proclus, this was known by Alice. Proclus says nothing about this one. It's quite strange for me, because we know that with these two couples, we know that 1,5 implies 1,6 and 1,6 implies 1,5. I mean, equality of angles implies equality of sides implies equality of angles. Equality of angles implies equality of sides. Okay. There's a question that comes to my mind. Why Alice conceived this and not this? Maybe he did, but Proclus says nothing concerning that. But what really puzzles me is not only this.
Sorry, I have a question, Carlo.
Yes.
So when you write E5 is equivalent to I5 is equivalent to I6, do you mean that if you have a geometry in which equality of sides implies equality of angle, then in that same geometry, so the two theorems as statements are equivalent one to each other?
Yes. Yes. That's the first thing I want to say, because there's something else I want to say. And I say this in the same way I raised this question. Because once again,
It's weaker. It says that in any geometry that satisfies 1,4,
Right? No, one,
1,4,
1,4.
1, 1, 1, 2, 1, 3, and 1,4,
okay. Then,
1,5 is equivalent to 1,6. That is 1,5 and
but wait a second, in
1,6,
geometry,
and
if you have 1, 1 to 1, 4, you get 1, 5.
but let me.
on this framework, the two are equivalent.
But Marco,
But they're both true.
Yeah.
So they're equivalent because they're both true. But to me, when you write that this statement is equivalent to that, it's different to say, you could imagine geometry in which this is not true, and therefore the other is not true as well. That's what I read in I5 equivalent to I6. You have two theorems here. And what you're saying is that one theorem is equivalent to the other. In other words, if it is true that equal sides implies equal angle, then it is true that equal angle implies equal sides. And conversely.
Because you have a semantic notion. Here, the point is that if you have 1, 1, 1, 1, 2, 1, 3, 1, 4, then you can, by 1, 5, you can prove Y6. And by
but Marco.
Yeah, but then it's not what is, that's not the same thing.
Sorry. I'm sorry to interrupt you. I would like to say something concerning what you claim, Marco, that 1,4, let's say, allows what follows. Okay, but let us remember the proof, and that is the reason why I wanted to sketch Euclidean proof, because 1,4, the version of 1,4 that is used to prove this applies to this triangle, remember, and this triangle. This angle is equal to this side is equal to this, and this is equal to this. 1,4. But, to say in modern terms, the orientation is different. We know that Hilbert has proved that we need to add something to 1,4. 1,4 is true, but not only in the case of the equal orientation, but it's true in case of different orientations. And what Hilbert proved is that if we eliminate this version of 1,4 and we accept 1,4 as a congruence theorem only for triangles which are equally orientated, if we restrict this version of 1,4, we cannot prove 1,5. Okay?
Right.
So, well, let me go. Now, in order to continue with this idea of the questions that come to my mind, let me put it in these very simple terms. What 1,4 allows me to say is that in two triangles, well, in one triangle, if I have two equal sides, then I have two equal angles, and vice versa. If I have two equal angles, then I have two equal sides. But once again, what puzzles me again is that anyone having seen this immediately should conclude that if you have a triangle with different sides, then you must accept that the opposite angles are different. There's no question. These are the propositions 118, 119. in Euclid's elements. And let me say something quite simple. According to Proclus, this was known by Thales of Miletus. This, it says nothing. Maybe it was known by Thales also, if we believe him. But these two propositions, according to Proclus, once again, these propositions were known, says Proclus, by Hippocrates of Chios. That seems to me quite strange. I mean, anyone knowing this should wonder what happens here. It's almost immediate. Maybe not the proof, but the question trying to say, well, something there's. Of course we know that from these two propositions that these angles are different. That we know. These angles are already different. The problem is what do I write here? That is the question. And we all know, we hope, we think, we suspect, the diagram tells us that the order of the inequality is the same. And vice versa. This is proposition from here to here is proposition 18. From here to here is proposition 19. Okay? So now comes an interesting question. These two propositions, we might say, should come immediately after these two propositions. It's exactly the question that raises. But there's a certain gap there. And the only reasonable thing that we can say is that the gap here exists because something that is proved here in between is needed in order to prove that the inequality sign here is the same that the inequality sign here. I mean, this gap is not an accident. Something really happens here in this gap. And so what I'm trying to say is that we have here two propositions which can be considered as guiding propositions. This would be the first step. This would be a second step. And this gap, this gives you an idea of what's going on in between these two things. Okay. I think I have said. Okay.
What you mean is that the proposition 1.7 to 1.17 are essentially lemmas for 1818?
Okay, broadly speaking. I mean, the thing, a lot of things happens, and it might be a little bit dangerous to say that the only thing that they were, the only reason why they were introduced is to serve as lemmas too. That would be something very strong to say.
But do you need them all to get 118? Do you need them all?
Well, somehow, yes. Let me tell you in which sense I mean this.
Not all together, but you
No,
know
no,
the
no.
change.
Okay, but you need all of them.
No, not really all.
Not
Not
really.
two, there is one that
17
is
is not needed,
independent.
12 is not needed, 14 is not needed.
Wait. For instance, in this,
But 14
Gap.
is needed only
you
with
have
our theory.
you have constructed the right angle.
Yes.
Okay.
Yeah.
You might say you do not need the right angle.
No, you need it.
Ah,
You need
okay.
the right angle, yes.
Okay.
Yes, you need it.
No, I'm sure. I'm sure that was what I was. No, that's what I was going to say.
Yeah.
That you need, in fact, the right angle in the two senses.
Yes.
Okay.
Yes.
So that's true. Okay. No, I was saying it's not completely. It's not exactly to say that all of the what is needed here is what is in between is really needed. I just trying to say to point out a certain, as I said, a certain path, a certain certain path to follow what is going on.
No, but, the only, if I remember well, in our notice, all is written clearly. But if I remember, well, the only one that is not needed is 114.
No. 17 is final, and
Sorry?
12 is final too. 117 is final. The 117 is not used in book one anymore.
117
Yeah,
also.
and 12
That
is
the
not.
two angles are greater than no. 117 is that two angles are less than two right angles.
Yes,
Okay.
and 12 is also final. It's not used.
Oh, okay.
Well, now, wrongly speaking,
Yeah.
I claim, well, you follow me,
Mhm.
you follow what I'm trying to say. Okay. Now, well, for instance, and it's not the only explanation, but for instance, in order to prove this, we need what is known as the exterior angle theorem. That is an important piece in the proof of these propositions, and it's proposition 16, I mean, is in between. And in order to prove the exterior angle theorem, some of the previous propositions are needed. Okay? So, okay. Now, after these two propositions, after when we arrive here, we arrive to this proposition 20, which was discussed somehow this morning, and which really is very, very interesting because what it says, in any triangle, two sides are always greater than the third side. What does it mean to say two sides taken together? Okay, we know that, but we know that in the ancient geometry, it was maybe considered as an axiom in the sense that it is a proposition so evident that needs no proof at all. Later, some modern geometers, let me say very competent geometers, as Poincaré, claims that this is a fundamental theory, to say that the straight line is the shortest distance between 2 points. For Poincaré, it's not a trivial thing to say this, to claim this, and to say that this somehow tells us something really interesting concerning the structure of space. Okay, but now, what I want to say is that the author of the elements says that we can now have the following conclusion, no, not conclusion, the following step. After this pair and this pair, we have, let me say this. You know what I mean? This side is equal to this side. This side is equal to this side, but this angle is not equal to this angle. If these angles were equal, the first congruence theorems would say this side and this side should be. But being different, the bases are different. And once again, the question is, we should say that we would like to prove this. In fact, let me be more specific. Right? This is proposition 24. And the converse, proposition 25, is claims exactly the opposite. So let me add these two propositions to this list. And let me say something concerning the triangle as a geometric figure. With these propositions, the triangle might appear to play a very interesting role concerning two geometric magnitudes which are involved in a triangle, which are the sides of the triangle and the angles of the triangle. And what does the triangle do with this? It plays a very interesting role since it tells us something about the way, let me say this, that might be something risky, but the triangles gives us the guarantee that some kind of increasing, decreasing relation between the magnitudes of the sides is equivalent to the increasing, decreasing relation of the opposite angles. Okay? That is what follows from here, and now from here. Okay? Here, we're in the case of the quality. Here, we're in the case of the inequality. And here, in the case of the inequality, and here we have the guarantee that an increasing, usually to say this, when the angle grows, the opposite side grows. When the opposite side grows, the angle also grows. And let me say this. Euclid is now, he has done really something really interesting. But he has a very, very hard challenge in front of him. For us, the challenge is something like that. Okay, then you should explain this increasing, decreasing relation. Tell me how the increasing angle somehow determines or says something about the increasing of the opposite side. That's a very difficult question. And we know Euclid certainly has no means to answer to this. Euclid is a very clever guy. Let me say this. He's a clever guy. Because in that point is when Euclid says, remember, we are proposition 25. Next proposition seems that it has nothing to do with what I've said before. Proposition 26 is the third congruence theorem. I mean, angle side angle theorem. Proposition 26. The third congruence theorem. Equal angle, equal size. The two triangles are congruent. Let me say something. This is, according to Proclus, once again, this is the only congruence theorem that Proclus says it was known by the pre-Euclidean geometric tradition. According to Proclus, this theorem was known by Thales. Known, exactly what does it mean? But just 1 second, just 1 second. Maybe this was known by Thales. But the only reason I believe in Proclus' theory is because I wonder, remember my first initial question, what was the version, what was the role, what was the sense of all these theorems, propositions, etc., that existed in the pre-Euclidean tradition. This might be interesting. According to the very old legend, which tells us how Thales calculated the Hadron pyramid, it involves the similarity of triangles. Okay. If I am a geometry who knows very well, knows the theory of similarity of triangles, as Thales certainly did, I ask about everything which is underneath this theory, I would conclude these angles are therefore equal, these triangles are therefore similar, but these sides being equal, the triangles should be congruent. What I want to say is that I am, of course, saying something completely different to what Euclid claims, but what I'm trying to say is that the possible version of this proposition, Thales' version, could have been this theorem as a particular case of the similarity of triangles, of the geometry of similarity of figures. Once again, Proclus says this was known by Thales, but we have no idea what the role this proposition played in Thales geometry. What Euclid says to us, this has nothing to do. This should be considered as a proposition which belongs to the theory of congruent triangles, not to the theory of similar triangles. Now, I was telling you that Euclid is in front of a very difficult question. Okay, now let me give a huge, big step, a huge step. Because after proposition 26, the relevant things that happens is the introduction. The postulate 5 appears, begins to play an important role. And begins to play an important role in order to say something about this particular geometric figure. We know that this is a very interesting geometric figure. Let me say this. It's a very decent figure.
Very
decent figure. It behaves very well. You can invite parallelograms to dinner at home. They behave very, very well.
I would prefer inviting someone else. But...
Yeah, okay. But no, let me say this. Parallelograms behave very, very well because of this. We know that, once again, in hyperbolic geometry, in elliptic geometry, they do not behave. And let me say, among this well behavior, is exactly what I was mentioning at the beginning of my talk. These two triangles are congruent in this geometry. Okay?
Sorry, here I am a little bit surprised
What?
because all what you said up to now seemed to me to go in the direction of arriving to the conclusion that was relevant in the first part of book one, is that the relation between the order relation of segments and the order relation of angles. Okay? And now you tell me that a parallelogram behave well because triangle and they half, when I was expecting you to say that parallelogram are well. Why? Because identity of the sides entails identity of angles. This is what in your line is to be natural to say, but it's not what you say.
Now, wait. Yes. What you just mentioned concerning the relation between angles and sides in this parallelograms, which is due to this.
Of course, you need that, but you need that exactly to continue the argument that you developed up to now.
Yes, but let me say one thing. This relation between angles and sides in a parallelogram, which is the one you mentioned, is due to the presence of this.
Of course, that's clear.
But this relation between sides and angles in triangles is independent of this. First thing. Okay. But remember, my dear Marco, that I left Euclid in front of, let me say, a big challenge. Explain to me how this, I said, increasing, decreasing relation of angles be explained in relation to the increasing, decreasing relation of the opposite sides. That was my big question. And I said that it's difficult to us to imagine what could be Euclid's answer to this. Maybe what I will say has nothing to do with this question, but it is in Euclid's elements. What do I mean? Okay, Euclid develops a lot of things as a consequence of this, related to parallelograms and related to squares. But in relation to squares built up from the sides of a triangle. Okay. Let me be more. Okay, and let me add also you see what I mean? this side is equal to this side, which is equal to this side. This one is equal to this one,
This is clear.
which is equal to this.
But it's not clear where you want to go.
Okay.
Bigger angles.
Remember that Euclid left us in front of the following question. I know this side is smaller than this side, but bigger than this side. This is proposition 2425. Okay. We ask Euclid for an explanation of what's going on. In our terms, give me the increasing, decreasing function. This is really an abuse, of course. Tell me something. Oh, sorry. You see what I mean? These two squares are exactly the same, equal. These two squares, which are exactly equal as these two squares.
Of course.
Sorry?
Yes.
But this square is different to this square, which is different to this square, which is 3. And that is exactly what Euclid explains. In this case, this square is equal to these two squares. Yesterday you were Googling and you found that, according to Google, this is the fundamental theorem, or one of the fundamental theorems of Euclidean geometry. Maybe you was not wrong. Because now what we can say, the only thing we can say is that this square is bigger than these two squares. And this square is smaller than these two squares. But what we know that Euclid did answer is how bigger than these two squares is this one. And how smaller than these two squares. I mean, the sort of increasing, decreasing relation is not given for the lines, but for the squares on the lines. This, we all know, is proposition 47. By the way, the last proposition of book 1. And these two, proposition 12, proposition 13 of book 2. So we have to go through the second book in order to understand Euclid's answer. But let me add something which is also very, very, very risky to say this. I said Euclid gives a sort of answer concerning not the lines but the squares of the line on the lines. Okay? If I draw here,
People that
okay,
on
okay.
Zoom cannot see.
I have to raise this, but well, I will conserve this. And I will raise it, I will put it again. So, let's say something which might be, I don't know how to say it. What I just suggested is that if you increase this angle, this line should increase, and the square on this line, should increase. Okay. Let me, first of all, let me ask you to be patient. And let us wonder what will happen in a sort of limit case. Sort of limit case. Let me put it this way. A, B, B. You have the triangle, the right angle triangle ADB, and the squares on the sides ADDB, AB. And let us imagine that we accept some kind of limit case. Exactly, you have understood, my dear Daniel. A, B, D, B. And I wonder what happens with the square on AB. And we know the answer. We know the answer from elementary school. Square on DB, the square on AD, no, something like that, because this rectangle and this rectangle should be equal. Okay? What do I mean? This sort of limit case tells me that the square on this side is equal to this square, Q1, which is 1, Q2, which is Q2, and these two rectangles which are equal. Let me put it in this way. In this limit case, we know the excess of the squares of this square over these two. What this proposition tells us is, in this sort of limit case, you already know that this square is bigger than these two squares. But I am telling you how much bigger is that. The excess is given by this rectangle. Is, let me say, well, I think it's had been discussed. Sorry. Here, I think it's better my drawing here. It's better, I think, my presentation. It's awful, but before arriving to this limit case, what will happen in the case of an obtuse angle? This square, we know, is bigger than these two squares. But what Euclid proves in proposition, I regress it, 12 of book 2, is that this square is equal. The blue square, which is this one, is equal to the green square, which is this one, and the red square, which is equal, but twice the rectangle formed by ADDB prime. Here, I should say, it was one square, the other square, the rectangle ADDB, which is this one and this one. This D, this B, is replaced by B prime. Okay? Euclid tells us exactly that in the case of the obtuse angle, this square is greater than these two squares, and the excess is given by twice the rectangle formed by AD and DB. And the same will happen on the other side, because what proposition 12 proves is that instead of going through the side AB prime, AD, I'm producing BD of AD up to DB prime in order to obtain Euclid's terms, the sort of shadow of this side DB upon the side AD, we could go on the other way. It's exactly the same thing. And I will not treat this, but proposition, this is 12, proposition 13 tells us exactly what will happen in the case of an acute angle. Okay? So, concerning the question that I raised, is Euclid able to give us this increasing, decreasing relation between sides and angles? I would say in a very different way, because he is taking the case of a right angle and the opposite side, but the relation he will explain is the relation of the square on this side and the square on these sides. The relation of the squares on this side and the relation of the squares on these two sides. In the case of the acute angle, the relation of this square and these two squares, and this gives us the excess. In the case of the acute angle, it will not be an excess, of course, it will be a defect, exactly. Okay? So, how much time do you have?
You have minus 20 seconds. Minutes.
Minus, okay, so,
Negative number.
Negative 20 minutes.
okay, well, I may just skip this. It is only to say that, well, in order to avoid some questions concerning, because I left the theory of parallelograms, the theory of squares, the last proposition of book 1, and almost the last propositions, the two last propositions of book 2, claiming that these propositions 12 and 13 of book 2 somehow close this inquiry, an inquiry that somehow began at the beginning of book 1, concerning the relation of sides and angles of a triangle. Now, concerning the relation of squares on the sides and squares squares on the sides of these triangles in relation to right angles and acute angles and obtuse angles, which is an answer given by Euclid in the book in the book 2. Okay, but in order to finish with minus 20 seconds, okay, let's imagine. Please, I ask you to agree for a moment with my way of understanding Euclid's elements. What happens in books 1 and 2? I am not claiming that it is the only thing that happens. What I say is that this could give us an idea of which path, which possible interpretation can we give to Euclid's elements. Okay, and at the very beginning, I just said that concerning the proof that Euclid gave us of theorem 1.5. And the previous proof known by Aristotle and certainly in the academic, the intellectual environment of the academia, Plato's academy. This was proved using properties of the circle, which Euclid does not accept at all. Now, we know that at the end of book 2, The next book is book 3, and we know, and I said this, it develops the geometry of the circle, geometric properties of the circle. Okay, let's imagine just for 1 second, I will not develop this completely. Let's imagine for 1 second that all that I tried to develop here was somehow in Euclid's mind. What could be the path of the geometry of the circle? Because we know that the path could not be the problem of the squaring of the circle. Maybe. The answer is here. You see? The case of the obtuse angle, the case of the right angle, and the case of the acute angle.
This is for the second volume.
Yes, because all of this requires a lot of stuff that will be proved by Euclid. In a circle, this angle is obtuse angle. It's not evident at all. Euclid will have to prove this. This is a right angle. This has to be proved. This is an acute angle. That will be proved. The relation, you remember the defect or the excess. Do you remember it was including this rectangle, A, D1, D1, B prime, which is exactly, I said, to be D1, D1, A prime. That is the power of the point D1, which is proved by Euclid in book 3. I mean, Euclid had this image in his head. I don't know. I will ask him in hell. As I said yesterday. I will ask him in hell. But what I am sure of, this recovers what I just said and shows us what should be proved in the geometry of the circle. Okay.
Are you sure that the Euclid will be in the hell and not in the paradise?
I hope.
Because you
So
said
why you're not gonna get to talk to him?
He's tortured,
okay.
2,000 years worth of
I was very good and I was not interrupted you, so now I have 2 questions for you.
A lot.
No.
Objections. Whatever you want.
2 provocative questions. So are you, implicitly speaking, are you telling us the 2 following things? First, triangle in book 1 behave essentially in the same way as circles. Are tools, not object to be studied.
No.
But that is, it suggested something like that. It suggested a triangular there to establish a relation of increasing and decreasing between angles and sides, and then to allow the constructed parallelogram and to go to the square. And so in the end of the story, they're not directly what we are studying. What we are studying are the relation between angle and angles and a square. So you suggested that. And so now you say no. So this is, okay, first question. Second, it is what you suggested also, you did not say, but also suggested, is that book 2 is a natural continuation on book 1. But to say that book 2 is a natural continuation of book 1 is also to say that Zeuthen was completely wrong. That there is nothing similar to geometrical algebra. So also that are you suggesting?
No. Well, In some sense, yeah, in some sense, yes, and in some sense, no. What I mean is the following. I do not reject any other possible interpretation of what Euclid is doing. In a sense, I have nothing against Soiten's interpretation.
Ok, no.
I have nothing against Soiten's interpretation of Book 2. I would say it's only, it is a little bit different from my interpretation. That is all. I mean, let me say, you see, there is a Mexican writer, which probably you know, maybe you, Jose, also know him, it's Carlos Fuentes. Okay, Carlos Fuentes, once he was in an interview, in a TV interview, and he said that he had the habitude to read the Don Quixote every Holy Week, every year. He said, I've done this all my life. Let's imagine he died when he was 80. Let's imagine that he began this when he was 20. That would mean that he read Don Quixote 60 times. Maybe so. Maybe. But certainly he was not an idiot. He was an intelligent guy. Maybe he read it 10 times more. Why should he knew exactly what was going on. He didn't read this novel once again to see if finally Don Quixote would defeat the windmills. Of course not. Let's say that being an intelligent man, he would accept that, well, I read this novel in some sense. Maybe I will read it and obtain a different interpretation.
So you mean there are 60 different Don Quixote in Don Quixote, and there are many different Euclid in the many different elements in the elements.
I am
what you
saying
want.
that maybe I have never read Don Quixote 60 times. I read it once, and I'm not sure that I will read it again. No, I mean, it's not the I mean, I would say, I wouldn't take Don Quixote as being the example of a novel that should be read several times. If that leads us to another conversation, but for me, there is only one. There's only one. There are several, but the novel that I will read more times. I don't know if 60, but as many times as I will be able to do it, it's not Don Quixote. You ask me what, which one?
Pedro Páramo.
No.
No. Okay, but
The Miserables of Victor Hugo. The greatest novel ever written.
good. But now let's speak Euclid.
Let's speak of Euclid. And what I am trying to say is that, okay, you can read Euclid according to Soiten, the way in which Soiten read it. Is he saying just stupid things? Not at all. Not at all. Not any everything he says. Well, it's acceptable.
But it's not the only.
It is not the only. I mean, I am here just suggesting a way to understand what's going on in Euclid's elements. Because one of the things that we were discussing today at lunch is that it's not easy at all to
Yes,
know
but,
what,
Carlos, your answer is is very politically correct in some sense, but is contradictory to an idea that it seems to me that is behind all what you are doing. What you are doing, if you understand, is not to understand what is in the element. What you are doing is why the element is as it is. And the why cannot be two, it can be one. There is all one reason. If the element is as it is because of Soiten reason, is not what it is because of your reason. So if you are really answering to the question, you are trying to answer why it is made that is made, you have to choose between your reading and Zoytan. You cannot say
Why
both
do
of
you,
them are
why
good.
do you have to choose one reason? I don't agree at all.
What I try to say,
you
I do,
write with one reason?
I do agree with the question.
Do you write with one reason and only one?
But, for me, it's already very difficult to write with one reason. If I
Exactly.
had to write with two reasons,
There might not
that
be-
would be
There might not even be.
impossible. But okay, Euclid was much more intelligent than me. So perhaps for him, there were two reasons at the time. For me, already having one book alone.
Marco, let me say one thing in order to give a more complete, possible answer to your question. Okay, I claim once again that my interpretation of Euclid is that a way to interpret, to understand Euclid. But it was not at all something that we should or could leave behind. But that's what I said at the very beginning. I mean, there is a lot of geometrical propositions that we find in Euclid's elements that, according to some commentators, early commentators of Euclid, Heron, Proclus, Pappus, etc., some propositions that were known before.
Yeah.
So my question, which I consider it's not a romantic question, but it is a historical question, is, okay, let us accept that Euclid took this proposition. It's quite easy to imagine that. But what I claim is that Euclid did something special with this proposition. Sure. Not only take them and copy them.
Sure.
He organized them in a certain way. He proposed an organization of a book, a geometric book, which is not an accident at all that it remains as the only book, ancient book that has come to us completely. Because we know about the existence of many ancient geometric texts. The one, for example, written by Hippocrates of Chios. We say it's a lost book. And I was discussing this today at lunch. To speak about the lost book, we should not think that it is lost because somebody forgot it in the subway or in the bus, left it. It is lost for some reason. For some reason, these texts, ancient texts, disappear. And I think, and I said this yesterday, and I think the responsible of this is Euclid. Because Euclid made somehow useless the previous geometric texts. Because Euclid took the previous tradition and introduced really new things.
So
And he produced the text.
The chance of Euclid is that the first time that someone made the element useless was when imprint was already invented. So it's Descartes. And if Descartes would, when Descartes made the element useless, print was already invented, so there was no chance that it was. Otherwise,
No.
Otherwise, also
No,
Euclid
no.
would have been lost. It's a very cumulative conception of mathematics.
No. But because I disagree completely, because I do not think that, I wonder, I speculate that Euclid made useless the previous geometric texts.
Not that Descartes made useless.
Exactly. That I do not agree. That I completely disagree.
Okay.
Because what Descartes did was a geometry of geometric locus.
And Hilbert made the useless. Hilbert made
No.
Euclid useless.
No.
So nobody made it Euclid.
Made it
Nobody.
comprehensive.
Carlos Álvarez, possibly.
No. On the contrary, what I am trying to say is to provide the way to propose a way to understand Euclid, and I just try to show the way in which I understand, broadly speaking, the way in which I understand what's going on in books 1 and 2, and at the very end, my last how do you say it? My last slide was to propose a way to understand what will happen, what will be what will be developed by Euclid in books 3 and 4. Because with this image in my last slide, we will recognize, well, everything is true, but there are at least 15 propositions, maybe I exaggerate a little bit, but a lot of theorems that will be proved and will have to be proved in Euclid's book 3 and 4. What I say is that when Euclid finished book 2, he made a drawing like the one of my last slide, and he said, now I know what will have to be proved in the geometry of the circle. The path is now.
Other questions?
So I just have a comment about what you said before. And Euclid never wrote why he decided to order the propositions in this way. But as if you read it and you think about it, many patterns appear. And Carlos today was speaking about certain patterns, certain propositions that seem to be guide for the other propositions. And then we will never know Euclid's reason. But we could see different patterns, and you could see a duck and I could see a rabbit, and both could be correct.
Perhaps it's not clear what I say. Of course, I agree. And this is very politically correct. And okay. But this is an answer to the question, what structure I could see in the book. That is a nice question that is an historian would wonder. And it's certainly a more interesting question than the simple question, what's written in the book. But there is another question that an historian can wonder, and it seems to me that is what Carlos wants to answer, that is what there was behind, what was Euclid's intention. Of course, this is a question that we cannot give a definitive answer. Sure, obvious, because we are not Euclid to ask him. But for me, it's a sensible question. And it's a sensible question that an historian should try to answer, even if he will never have an argument for the final answer. And it seems to me that is the question that you ask, is not what pattern I can find. But the question is what guided Euclid to write. So the politically correct answer is not
what kind
a
of
good answer.
evidence would you need to answer this question?
I tell you when I try to answer this question what I do, what I did, because now I stopped to make history of mathematics. Let me finish. Then you go. When I made history of mathematics, the exercise that I always did was the following: take a book, read 10 pages, and then close the book and try to write the 11. If I understood the 11th page was the one identical to what I have wrote. If it was not, it was different, so I did not understand the first 10 pages. This is an exercise that I always did. Try to anticipate one page. So you can do that. It's not a definitive answer, but it's an answer that you have an argument that allows you to tell that the last page is the one that you imagine, so possibly you understood the intention.
Let me just add one last remark. And I think, well, okay. Let me take a simple example, which I mentioned. Proposition 4 of book 2. Proposition 4 of book 2 is this one. This one. Okay. It's kind of Zoiten's interpretation would say, and at least it was the way in which I learned in elementary school, the law of the square of a binomial.
Mhm.
It is the clear example. It is and maybe it is a very good and very pedagogical example. It will give us, in this sense, the strong argument to say that Euclid was doing something like geometric algebra. Okay, well, some people would say that. Okay, it's not far from Zoiten's interpretation. Okay, I do not reject completely this possible interpretation, but let me say that I said something quite different, which has nothing to do with the binomial law, the square of the binomial. What I said is Euclid is trying to show here, to prove here, to find here the maximal excess of this square in relation to these two squares. That is the point. That means this does not at all reject the possible interpretation of Euclid as a book written within the idea of developing some kind of geometric algebra. But what I want to show is that we can understand this theorem as trying to give us the maximal excess, because there is no doubt that Euclid is looking for how this square in this proposition 47, the Pythagorean theorem, this square is equal to 2, and if the angle is obtuse, the square should be greater. If the angle is acute, the square should be less.
So
And that is what
I want to try to understand what you guys are arguing about. So it seems to me that what you're arguing about is, as we try to understand what was the intent of, or what was the driver of Euclid, what you're saying is that that's a sensible question. People can give different answer, but ultimately there is only one answer.
Exactly.
That's your point.
Exactly.
While I guess,
Even as we'll never know which is,
which
but
we'll
it's
never
only
know,
one.
which we'll never know. While I guess the other attitude, if I'm correct, but I don't want to put words in your mouth, is that you can have multiple ways to interpret the same.
So, what I'm saying is a little bit weaker, and it is maybe Euclid had one intent, but the kind of evidence that we need in order to be sure of the intent is some kind of evidence that we do not have.
Right.
We do not have anyone talking about it, not himself, not his students, if he ever had any. So we never will know what was the intent. We could just try to examine the book. We could try to find patterns. Marco's way of finding a pattern is a very interesting one, but it is not the only one. And
So
it is
you're
just
like a quantum
one way.
physicist. Your position is that there is no real.
There is no real.
We don't know the position and the velocity of the particle.
We cannot know unless we
Is
open,
a
we
quantum
go into a cave.
He's a quantum physicist, I am a Newtonian physicist,
Yes.
which is not surprising,
Yeah,
right?
it's not surprising at all.
maybe what I would say is that the only thing I can say is finish with the very first thing, the very first quotation.
Yeah.
It was at the beginning of my talk.
And I guess that my view on this is that while you may be right, Marco, it's, I actually tend to believe like you that there is one answer, that's the end of it. But it's almost the wrong point to take because it doesn't really matter because we don't know. We cannot discover.
Except,
we can present different.
Sure, except for this fantastic idea of Max Weber
Okay.
that wrote once something that has already been the guide of my life. Nobody will arrive to the very few that is possible if we do not try to go to the impossible. So
And that's
that
what I-
is all. I know that it's impossible to do what I want.
It's a question.
But it's exactly because I want it's impossible that I hope that I will
Okay.
get something interesting. Sorry.
Oh, no, it's fine. Totally different question or line of thought. This is very broad, but I was wondering, it seems the arithmetical books, the structure of the arithmetical books in the Elements is much less clear than those of planar geometry. There are no axioms, there are no postulates, evidently. And it seems like your approach might be a really nice way to give some kind of structure to the arithmetical books. I was wondering if you've thought about that at all, or if you think this kind of thing can be done.
Yes.
That would be very attractive.
Yes. I've worked on the arithmetic books.
Okay.
And starting from what you just said, there's no clear axiomatic framework. Let me put it in this way. That's true. There's no question to say about it. However, I think that just to suggest an answer, because that would lead us to another talk completely. I think something should be really said concerning the arithmetic procedure, the arithmetic, the Euclidean algorithm, which is introduced by Euclid in the very first proposition. In a way which is quite strange. What do I mean? In the first proposition of Book 7, Euclid says something like, imagine you have two different numbers, one bigger than the other, and you subtract the smaller from the bigger, and imagine that you can repeat, etc. And he's describing the algorithm. And he says, at the end, if the procedure ends, because it should be with a unit, the initial numbers are prime among them. Second proposition, if they are not prime another, you made another, again, this procedure, this algorithm, and the end could not be a unit, then you get a number, and that will be the greatest common measure. What I want to say is that concerning your particular question, I think that the Euclidean algorithm plays a very interesting role there in the arithmetic books. Okay.
May I ask a question?
Yeah, there's a question on Zoom.
Yeah. Hi. Well, first, there was a.
For I don't know for which reason, but we can understand you. You can go.
Okay. So
A moment. So
my first was a remark that when you were saying that the triangle that can be made into this parallelogram is specifically Euclidean. Well, I don't see it that way, because you could get the midpoint of a side and reflect the other vertex into it and get a parallelogram, and that's absolute. So there's no need for that. But that's a minor point. And then the other one would be that because you have a reading of this, have you considered also the fact that the propositions 1 through 28 are absolute? And what do you think of Imre Toth's thesis that the structure of Book 1, including with some fragments in Aristotle, tells us that there was serious concern about alternatives to the parallel postulate, because else why would Euclid mention propositions 16 and 17 of Book 1, which are totally trivial once you know that the sum of the angles of a triangle is 2 right. So these make sense only if you value absolute geometry. And I'll stop there with a question and comment.
Okay, can you hear? Okay, okay. Well, first of all,
Yes, I can hear.
okay. Well, first of all, yes, a lot of has been said concerning this, that the first 28 propositions belong to the absolute geometry, and somehow after proposition 29 really is the beginning of really Euclidean geometry, because before we have developed only absolute geometry. That is true in some sense. Well, that is true. What I was trying to say is that first, Euclid needs the postulate, the parallel axiom, in order to obtain what he wants to obtain, in order to prove what is needed to be proved about parallelograms. What I just said, maybe joking, that he needed that parallelograms behave well. That well behavior of parallelograms is due to the parallel axioms. Behave well, that means particularly exactly what is needed. I do not completely understood your remark concerning the way in which a triangle could be completed to a parallelogram.
Yes, Victor, I think that the problem is not he did not understand. It was not completely clear what you said by the.
Okay,
Can
well,
you
let's
repeat
see.
the first remark about that? It was also for me. It was difficult to understand.
It's really easy. I'm not sure that I can share here things, but if you allow me to share, then I can show you really.
I think you should be able.
Okay, great. Then here
Right.
I'm sharing. Okay, so you will see a whiteboard on the screen, and it's really trivial to explain what I mean. Is here I have a triangle, right? And I want to get a parallelogram. Well, I get a midpoint. That's a very absolute operation. I reflect this into this, and here I have my parallelogram. And proving that this is twice and all this stuff is all absolute. So there's no Euclidean
But you cannot prove that this is a parallelogram without the postulate 5.
What does it mean that it's a parallelogram? What do you mean by that?
That lines do not intersect, that opposite lines do not intersect.
Oh, this is very absolute. One doesn't need anything for that. One can prove this in absolute geometry, no problem.
I do not know.
So you prove that these are parallel. What you do
Yes,
not
one can
prove-
easily show that these things, this is parallel to this, and this is parallel to that. One doesn't need any Euclidean thing here.
Okay, I guess that what you cannot prove is that if you start with a parallelogram, then if you divide it into 2, you're going to obtain equal triangles.
It's not clear what a parallelogram is in that sense. Yeah,
It is
if you just start with an incidence definition of parallelism, certainly not.
Okay,
Yes.
okay. I see.
But are you sure that the opposite sides are equal without the proof of the opposite sides being equal? Is independent of the parallel axioms?
Everything you have in Euclidean is true in absolute in this thing. I mean, it's really easy. There's nothing Euclidean in this. In showing that I can take any triangle and flip it over and get a figure that has twice the area of the original one. And this figure, whether you want to call it a parallelogram or not, doesn't matter really.
Okay,
Thank you.
okay, thank you.
So now I can stop sharing and that's it.
Yeah. Victor, independent of Euclid,
Yes.
insofar you are here, you know that we always wait for you here. We have only to say when you want to come, you are more than welcome.
Thank you.
And about the other question, oh, he left. Okay, so.
No, it's still there, 3.
It's still there. Okay.
Victor, are you still there?
I'm still here. I thought that
Okay,
I
Okay,
should
okay,
mute
so I
myself.
couldn't see you. Okay, so you asked about proposition 16, right? But 16 is used in 27, and this is used in 31, which is used to prove 32, which is the sum of the interior angles is 2 rights. So 16.
But you can do it very easily without that.
Oh, I didn't know that.
Yes, there's absolutely no need. I mean, if you're going to teach today, you're not going to do these things, and you don't need the external angle greater than those. You can do. I mean, you just draw your parallel. It's the classical proof here. Let me share again.
But
Okay.
let's say there's a problem with 116 because it's not completely absolute.
What is 116? I don't remember. What is 116?
I mean, 116 is not true in spherical geometry.
Let's see. Okay,
Ah.
here I am.
No. Okay, but it's
Let me show you
no
why
absolute
it's so.
geometry.
So 116.
We speak of absolute geometry.
Yeah.
Spherical geometry is not part of absolute geometry. Absolute geometry is Lobachevsky plus Euclid. Plus, okay. It's common to Lobachevsky.
That means it's not true also in elliptic geometry.
No, of course. In absolute geometry, we are speaking absolute geometry.
So let's see. So you're saying these. What is 16? I'm getting my copy here, so I'm not saying nonsense about this. 16 is saying if in any triangle, if one of the sides is produced, then the exterior angle is greater than either of the interior and opposite angles. And 17 says in any triangle, the sum of any 2 angles is less than 2 right angles.
Yeah.
Yes.
And I'm saying that no sane person would state this if you're doing Euclidean geometry, because they are trivialities.
Yep.
And the reason they're trivialities is here is the easy proof of the sum of the angles that everybody does. Is you're taking one vertex of this triangle and you're drawing your unique parallel that exists because you're in Euclidean geometry. You also have a theorem that says that this angle is the same as this, that this is the same as that. And so you see the sum of the 3 here is 180 and we're done. There's no need for those 2. So the only reason why you would have those 2 is that, according to Imre Toth and so on, is that they were really aware of the need of the parallel postulate as an axiom because they had looked at, geometers of Aristotle's time, because they had looked at denying it and where are you getting? And because they didn't like where they were getting, they decided to take it as an axiom. And these first 18 is that are there because they are absolute and because he was aware that there is a greater value to them if you're not using the parallel postulate. So because you were talking about intentions, I thought that that's something else that one may be adding in possible intention in the 60 possible readings.
So the point of Imre Toth that you are in some sense presenting here is that Euclid saw in some sense a possibility of a rich geometry independent of
Correct.
postulate.
Correct.
And that is different to what Carlos says. Carlos says that Euclid tried to simply use fifth postulate when is needed. That is, there is no idea of a geometry independent, but try to do what he can without the postulate. And when the postulate is needed, he apply it.
Yeah, I
So
understand
there are
that.
two
That's
different
clear.
readings. Of course, there are two different readings.
It's
Yes,
totally clear that he needs his postulate to get to the later books and everything else. But
well,
there was a debate that, you know, that the fifth postulate is fake, that it has been interpolated and so on, that, you know, nobody ever needed it and whatever. And the structure of book one tells you that that's not the case, because no sane person would say 16 and 17 because they're totally useless. And unless you want to create a body that is clean of the parallel postulate, there's no need to do this stuff.
but let me say just one thing, and this is not a complete answer concerning your concern, but I agree that Euclid needed the parallel axiom, that he knew it was needed, because concerning what I tried to explain, you need the parallel axiom in order to construct a square.
Yes.
If you do not have the parallel axiom, you cannot be able to construct the square.
That's sure.
And what I try to say is that at the very end, well, in the second stop, squares play a very important role in Euclid's path, according to the way I try to develop. So certainly Euclid needed the parallel axiom, not in order to draw a line between a geometry with parallel axiom, a geometry without parallel axiom. I mean, maybe yes, maybe no. It's not.
Yeah, of course, these are two different patterns.
Yes.
Different.
What I'm saying is that certainly Euclid needed the parallel axiom, of course, clearly stated, in order to, particularly concerning what I said, he needed it to construct the squares. Without parallel axioms, you do not have squares.
Victor, I don't know whether you read in all books in all languages. So I don't know whether you read the Spanish version of Carlos' book. One of the things that Carlos developed in this book that he did not repeat so explicitly today is that one of the aim of Euclid in the first four books, not only in the first and the second, is to develop a large corpus of geometry independent of proportionality.
Yes.
To show that there is a large geometry that is independent of proportionality. So in some sense, this is the same idea that thought had, but in another point. So what in thought interpretation, he tried to develop a large corpus of geometry independent of postulate 5, sorry. That is another pattern. That is not what Carlos
Yes, exactly.
suggested.
Yes, I understand. No, I was just wondering if Carlos gave any thought to this problem. And it's not, we're always saying Euclid, it's pretty obvious that he got several books from previous things, like the theory of the even and the odd, that's clearly Pythagorean. I mean, Neuenschwander had analyzed this text and figured out which pieces are from where. I guess everything is debatable, but the thing is that you have these fragments in Aristotle that tells you that these concerns were there before Euclid, and he probably put these in because they were in previous elements because of the same concerns. Because else, as I say, if you're just interested in doing Euclidean geometry, I'm sure that Euclid knew better ways than having to say 16 and 17, which are trivial consequences of the sum of the angles being to the right. So that's
Perfect. Okay. Other questions, remarks? So thank you to, a question there? Go.
I had some trouble following whether you're claiming that congruency is supposed to be more fundamental in Euclid, and this is one of his
Well,
novelties.
Sorry, I didn't understand your question.
So maybe I'm misremembering what you said yesterday, but between yesterday and today, it seemed that congruency, you're saying, is supposed to be more fundamental in Euclid than it had been treated before, more fundamental than similarity, or that Euclid.
No. I wouldn't say that.
So I
I wouldn't
misunderstood.
say that it is more fundamental. I would say that it comes before, and according to Euclid, it should be developed before the similarity.
Independently. But
Before-
in some sense, you say that it's more fundamental because you can develop incidence without similarity, but you cannot develop similarity without incidence.
Yes, that in some sense, they claim that for Euclid, the congruence becomes a notion, a concept that should be studied, developed, etc., before the similarity figure. That is clear. And historically speaking, that puts us in front of a huge question. Because according to the legend of the origin of geometry, that takes us back to Thales of Miletus and his calculation of the height of a pyramid. Geometry, if it's true that geometry began around that, we should say, well, geometry began developing with the relation of similarity. And the interesting stuff is that Euclid said, okay, that may be, but the reorganization that is needed in geometry is such that this relation, which maybe historically was the very first one we began to study, it should be postponed. And it was not postponed 3, 4, or 17 propositions. It is postponed 5 books. It's quite late, the way in which Euclid says it should be pushed back. 6 books. Okay.
Thank you. Thank you very much. Thank you.